Welcome back to this practical quantum computing course. In this lecture, we will get familiar with some useful properties of quantum systems, which will be put into practice in the future lectures about algorithms implementation. In particular, we are going to introduce the ancillary qubits, or ancillas, and a particular practical example of how these can be used to perform some operations on a qubit system. When we take into account a complex algorithm, like will be Grover or Doi-Jozsa, we can need many qubits to perform some tasks. We typically refer to the main qubits of the system as input register. On the other hand, it can be useful to consider some more extra qubits, which can be used as support of the input register. There are many situations in which ancillary qubits are useful. So let's make a list of 3 at least. So imagine at first that you have a system of qubits and you would like to implement some complex operations which requires more computational power. For example, let's imagine you have just 2 qubits and you would like to implement a gate in which you use both of them as control qubits. In this situation, you will need an extra qubit to be used as target. It will be the ancilla. Okay, let's improve the previous example. Let's imagine now you were able to apply your multi-control gate. And you also created entanglement between the ancilla and the system. Now you can extract information about the input register directly from the ancilla, because the ancilla spoke with the system, without applying any measurement gates on the other qubits. This will leave the system unchanged, but you will still have your information. Last but not least, nowadays we have access to noisy quantum computers. One of the most promising approaches to clean the devices from the noise is called quantum error correction. So now we are not going to discuss details about quantum error correction, since another set of lectures will be released about this topic. But we can say anyway, that quantum error correction algorithms typically require a set of qubits, ancillary qubits, to protect the state of some more inner part of the device, that is typically the input register. Okay, now let me introduce you to the practical example, the phase kickback, which is an algorithm, a very simple one, in which we apply an operation on an ancillary qubit using the input register as control. As you will see, this operation will incredibly modify the state of the control qubit itself, leaving the ancilla untouched. This is the reason for which it's called kickback. And now, before putting our hands on the code, let me delve deeper inside the definition of the phase kickback problem. Before describing the details of the phase kickback, it is important to make a premise. We are going to manipulate the phase of the input register with a kickback mechanism, which makes use of the extra ancilla qubit. This can seem weird because we are using 2 qubits and a control gate for an operation which may simply require 1 gate directly applied to the input register. Well, there are many reasons for which the approach we are going to see is important, and one of them is that usually it's a good practice not to interact with the input register until the very end of the algorithm. Secondly, in the next lectures, we will make use of the phase kickback trick while implementing some important algorithms, like Doi-Jozsa and Grover. Now, let's talk about this phase kickback. Firstly, let's consider 2 qubits. The first qubit will be the input register, while the second qubit will be the ancilla. We want to build an algorithm in which the input register acts as control qubit over the ancilla. In particular, we will implement the following steps. 1. We initialize a circuit of 2 qubits, both of them prepared by default into the 0 computational state. Then we apply an AND gate to the input register, which prepares the maximally superposed state. Then we apply a NOT gate to the ancilla, and the reason of this step will be clearer soon. Now, an important requirement. We select a control gate, which will be applied on the ancilla, using the input register as control. It is important to select a gate for which the state vector of the ancilla is an eigenvector of the gate. This is the core part of the algorithm. In our case, we choose a gate which has the computational 1 state as eigenvector. Indeed, we prepared the ancilla with a NOT gate. At this point, we apply the gate. As you can see from the algebra, using a qubit in a superposed state as control qubit leads to a new state in which we have a coefficient which multiplies only the part of the state for which the control qubit was in the state 1. The final formula shows that the state we get is still factorizable, and in particular, that the state of the ancilla is untouched. This modification raises a relative phase term which affects the part of the input register which is in the state 1, which is not detectable at this stage if the measurements is done in the computational basis. To visualize this effect, we just need to apply another Hadamard gate to the input register. This will create interference between the state and will allow us to detect the phase manipulation. This is the way we can implement the phase kickback. But now, let's put our hands directly on the code. So, as usual, now we can start by importing some useful functions and models from Qibo. For example, from Qibo, import circuit and gates. And then we also import a plotting function that will be useful to plot the probabilities of the single states that are going to compose our final state from a Qibo state object. So from scripts.plot scripts import plot probabilities from state. Okay, now we can set the backend after importing Qibo also. Import Qibo. So we can say Qibo dot set backend, and as usual we set Qibo JIT as backend. Nice. Now we can start implementing the circuit that will be useful to see the phase kickback trick in practice. So we just need to define a circuit, C equal to circuit. We just need a couple of qubits. And then we prepare the initial state that has to be 0 for the input register and 1 for the ancilla. So we add a gate, which is a NOT gate, just on the ancilla, which is the qubit number 1 in this case. We don't need to apply any gate to the input register because by default the state is initialized to be in the state 0, the computational 0 state. At this stage we can print what happens if we execute the circuit. And as you can see, we have a state that's the 0-1 state. At this point we just need to check which kind of gate we want to apply to the ancilla in order to have the phase kickback trick. In the next cell, we are going to apply an Hadamard gate to the input register. After this, what we want to do is to apply a control gate to the ancilla. And it is important at that stage that the state of the ancilla is an eigenvector of the gate we want to apply on it. So, in order to do this, let me just check which kind of gate we can apply on the ancilla, and if the state 1, that's the state in which the ancilla is now, is actually an eigenvector of the gate. So I would suggest you to start from the T gate, and now I will show that actually the T gate has 1 as eigenvector. So what we can do is to just initialize a dummy circuit with 1 qubit, circuit 1. We add an X gate, we prepare the state of the qubits because we have only one qubit, to be in the one state. So c.add gates, so c.add gates dot x applied to the qubit 0, and then we print the state, and it should be in the one state. So C executed. Okay, we have the one state. Now we add also a t gate. So c.add gates.t applied to the 0. What happens is, as you can see, is that we are modifying the amplitude of the state, but the state remains the 1. So this is exactly what we expect from an eigenvector. Now we can have a look to this function here we already wrote for you. Basically, we already implemented the phase kickback trick. This function is quite more complex in the sense that we want to be able to activate the kickback trick or not. And so we are just passing this argument here, which is kickback, and you can set it equal to true if you want to apply the phase kickback, or false if you don't. So what we have here is just a circuit with 2 qubits, like the one you saw before. Then in the following line, we apply the NOT gate to the ancilla, preparing the initial state 0, 1. Then we applied, according to the phase kickback trick, an Hadamard gate to the control qubit, which is the input register. After applying the Hadamard gate to the input register, then we can decide if kickback is equal to true, then we can activate the phase kickback trick. And we can do that by adding a gate, which is a T gate, applied to the ancilla, as you can see here, controlled by the qubit 0, which is the input register. Now, what we can do is to add the final Hadamard gate required by the phase kickback trick, as you already know, and finally we can add the measurements gates. We add 2 measurements gates to both the qubits. Then in this function here, we just parse the final object, which is an outcome object. We receive if we execute the circuit with a number of shots, in this case is 1000, and then we return the outcome. So the aim of this function here is to define a circuit according to the phase kickback introduction, and then we apply or not, depending on the kickback Boolean variable, the kickback, and then we return directly the outcome object. So what we can do now is to check what happens if we set kickback equal to false or kickback equal to true. Perfect, now we can execute the circuit, collecting the outcome into an outcome object. Outcome equal to execute circuit, and then we set kickback equal to false for this first example. Then we can print the state, so print outcome, and also we can plot the probabilities using the plotting function we already imported. So we can use plot probabilities from state, and then we should pass the Qibo state object, and the way to do that is just to call outcome dot state. What is happening here? So as you can see, we have still the initial state. So we started from 0, 1, then we applied a couple of Hadamards to the qubit of the input register, and so basically we did nothing on the qubit, and what we get in the end is the 0, 1 state. If you want to see it in terms of probabilities, you have the final probability to get the 0, 1 state equal to 1. Now we can see the same, but setting the kickback equal to true. So again, outcome equal to execute circuit, but at this time we set kickback equal to true. So what we expect is now that we are applying a control gate on the ancilla, controlled by the input register, which is in the superposed state, and we expect to have some modification of the amplitude of the input register. Again, we can print the state, so we can say print outcome, and we can call the plotting function, plot probabilities from state, outcome dot state. What we have now is a slightly different situation. So as you can see, the final state now is quite different. From the explicit definition of the state here, you can see that the qubit number 1, so the ancilla, is always in the 1 state. So basically we didn't touch it. Otherwise, the input register is now moved a bit from the 0 state to the 1 state. The same you can verify if you look at the plot. Indeed, now the probability of getting 0,1 is no more 1, but is something around 0.8, and we have some probability to get the state 1,1 arising. This is what we get by applying what we call the phase kickback trick. So the qubit in the input register tried to apply something on the ancilla, but the effect of this kind of action is that we get some modification of the amplitude of the input register itself. Now we want to propose you an exercise. Can you find a control gate, CG, which applies a larger kickback effect than CT? So, in other words, we want you to replace CT in the previous circuit with a gate which reduces again 0,1 and increase the amplitude of the 1,1 state. And now we can go on and complicating a bit the situation. Indeed, what we want to do now in this very last part of the lecture is to add another argument to our execute circuit function, which enables us to repeat the execution of the circuit in which we involve the kickback trick many times we want. So the idea is now to say, okay, but if we one-phase kickback trick, I can move part of the 0,1 amplitude to the 1,1 amplitude. Now, if I repeat it maybe 2, 3, 4 times, what happens? Maybe I move more of 0,1 into 1,1? The answer will be yes, as you are going to see in some minutes. And the way we implemented this is just to pass an extra argument to the execute circuit function, the n times argument. And then after you have prepared the state, as you can see from the first line here, you prepare the circuit into the 0,0 state, then you add an x gate to the ancilla, so you have 0,1, and then you loop over these n times, and you add the phase kickback trick, how many times you want. Finally, you add your measurement gates, and then you execute the circuit, and we basically do the same we were doing before. So now the execute circuit is modified. We can go up. We just copy paste what we typed before here. And so now what we are going to do is to add in the execute circuit just an extra argument n times, and we say equal to 2. So what we expect is basically something very similar to the case before, but now we want the state 1,1 to be larger. And indeed, what you see here is a different kind of state, in which the 1,1 has the same amplitude of the state 0,1. So you can imagine that if we go on with this kind of procedure, for example by setting n times equal to 3, the state 1,1 will become larger and larger with respect to the state 0,1. Until at some point, if we set, for example, n times equal to, let's say, 6, what happens is that we start to reduce the amplitude of 1,1 and coming back to a situation in which the state 0,1 will be pushed to be larger. These kind of results are useful because you see a sort of periodicity in the behavior of the system. And this is exactly what we are going to face in a future lecture, the one of the Grover algorithm, in which we are going to search for a specific solution in a set of solutions, and as you will see, we will have some optimal number of times we need to execute the algorithm to find the solution in a periodical scenario. So this ends these lectures about the phase kickback, and we can now move on with the next lecture about the Doi-Jozsa algorithm. So in this lecture, we experienced the phase kickback trick. That's one of the ways we can use the ancillary qubits. And now what we saw in a very dummy example, we want to put into practice in some more interesting algorithm definition. And indeed, this is what we are going to do in the next lecture about the Doi-Jozsa algorithm.